Hi, in today's video we're going to be talking about substitution reactions and the mechanisms of how these operate. So when you have a nucleophile interact with an electrophile, you can push the electron arrows and form a new bond between the nucleophile and that electrophilic carbon, and you kick off the leaving group. If you want to know about leaving groups, look at the past video. So when you do this, you can think about this from an energy diagram perspective, where you're starting from A, that is these molecules in the starting material, going to B, and they're going over a single transition state. So that transition state, intermediate, ends up looking pretty close to planar. So this carbon in the middle is roughly planar, and it has a little delta positive, meaning it has a little bit of positive character. The iodine, as this bond is being broken, has a little bit of a delta negative, so it has a negative charge build up. The nucleophile comes in with a negative charge as well, so there's a negative charge buildup on that side as well. And so again, this molecule kind of forms a direct line between nucleophile, carbon that you're making the bond to, and the iodine. Another key feature of this is as the nucleophile approaches the carbon atom, it ends up inverting the carbon atom, kind of like inverting an umbrella in a windstorm. So let's look at the kind of bonds that we're making and breaking. Actually, before that, I will point out that this is called an SN2 reaction. The reason it's called SN2 is that there are two molecules that are involved in the rate determining step in this transition state. So let's look at the way that these the bonds work for this particular kind of reaction. So if you look at the carbon-iodine sigma bond, the nucleophile cannot interact with the sigma bond because there are already electrons there. So instead, it's going to interact with the sigma star, the antibonding orbital. The antibonding orbital is found exactly opposite of the carbon-iodine bond. So if we redraw this molecule with all the atoms in the same arrangement, you see that the antibonding orbital, the carbon-iodine antibonding orbital, is found directly on the opposite side of the carbon as the iodine. So as the nucleophile approaches this antibonding orbital, these hydrogen atoms become planar, and that is energetically costly, and that is why you end up having this kind of higher energy transition state. Let's now look at some examples of these substitution reactions, SN2 reactions. The first is with this nucleophile sodium azide and this propyl chloride. So whenever you're given a reagent like sodium azide, you can pretty much cross out the sodium because that is not going to be the nucleophilic portion. It's the azide, the negative charge on the azide, that's going to be the nucleophile. Because this is an SN2 reaction, it's happening all at once. And so you're forming a bond between the nitrogen of the azide and the carbon, and the chlorine is now leaving as a leaving group. But I'm actually drawing it as a salt because you had sodium around all along. Now when you replace this particular molecule that has a stereogenic carbon, so the bromine is coming out at us, you note that the azide now inverts the stereocenter and gives you the opposite handedness of this particular molecule. That is a hallmark of SN2 reactivity. Again, another molecule we have where we have this secondary alkyl iodide in a ring form, and we had a new nucleophile here, a cyanide nucleophile, and cyanide can again displace this iodide and give you inversion of the stereochemistry. Finally, we have this tertiary alkyl halide, and we're going to try adding sodium cyanide to it, but unfortunately, the tertiary center is too hindered. So again, the nucleophile has to approach from the back side of this particular molecule to achieve the bond it has to give its electrons into the antibonding orbital, and that antibonding orbital is simply too hindered by the other carbon and hydrogen atoms that are around. So don't do an SN2 reaction on a tertiary alkyl halide. Let's now turn our attention to the SN1 reaction. So the SN1 reaction, unlike the SN2 reaction, first involves the removal of the breaking of an alkyl halide bond to form a high energy carbocation and a halide. So from an energy perspective, you can see you're going from A to B and you're going way uphill in this high energy intermediate. Now something can come along as a nucleophile, in this case it's the water, the bulk solvent that's around here, and when the nucleophile forms a new bond, you get compound C, and then eventually that compound will lose a proton to the bulk water and give you compound D. I want to point out that this is the rate-limiting step. This formation of the high-energy carbocation is the rate-limiting step, and that's why it's called SN1. There's only one thing that's involved in the rate-limiting step. Let's look a little bit more at the nature of the carbocation. So if you look at this carbocation that came from T-butyl bromide, you'll see that it is planar. And because it's planar, the nucleophile can actually approach from either side. So this means that if the molecule had a handedness or a stereogenic carbon at that position, you're going to lose that stereogenic or that chiral information. Let's look at some examples. So again, we have this tert-butyl iodide reacting with methanol. You would predict that you would form the oxygen as a nucleophile to carbon bond, and the remnants would be HI, which is again a strong acid. That gives you somewhat of a hint about the types of conditions that these reactions are run under. Again, we have another tertiary halide, alkyl halide. Remember, the SN2 reaction didn't work in this case, but the SN1 reaction does work. I'll point out that now that because we had this planar carbocation that was generated when the halide was gone, the nucleophilic water is going to approach from either side of the molecule. And again, you'll have the remainder of HBr as the acid. And you'd likely get a 50-50 or about a 50-50 mixture if you started with a single enantiomer of the starting material. In this case, we have a primary alkyl halide with water, and you would not predict that reaction is going to work simply because this primary carbocation is not stable. And so I want you to eventually watch the video on carbocation stability to understand how you could predict these various stabilities. Let's look briefly at the solvents and conditions that are found in SN1 and SN2 reactions. So polar protic solvents, you saw those a lot in the SN1 reactions, and let's see why. Well, they're able to stabilize anions and cations, and so that they often help to allow for SN1 chemistry to occur. These SN1 reactions often require heating, and they're often, or almost always, under acidic conditions. The other types of solvents that we'll encounter in this book are called polar protic solvents. So in this case, we have acetone, dimethyl sulfoxide, THF, and NN-dimethylformamide. So I will point out that these solvents, most of them have abbreviations. So acetone we've talked about before, but dimethyl sulfoxide we just call DMSO. Tetrahydrofuran, instead of writing that or having to say that, we'll just say THF. And the NN-dimethylformamide is abbreviated as DMF. So these are all polar aprotic solvents. And these are types of reactions in these solvents are often SN2. There's lots of other reactions as well we'll see in this book that are not necessarily SN2 or SN1, but reactions that are SN2 are definitely going to be found in these types of solvents. And these reaction conditions for SN2 are generally basic, so that's another key or clue that you're dealing with an SN2 reaction. Thank you for your time, and I look forward to seeing you in the next video.